Yes. So, you ready for the last talk this morning? And before I start, I would like to say that I'm a theoretician. I guess you figured that out last time. And again, I'd like to keep this very informal. You can ask questions anytime. And also, I don't need to cover all my slides. When you do theory in this field, there are like some techniques that you should master. You need to be able to solve the time dependent working equation in some way. You need to be able to understand Maxwell's wave equations if you want to do propagation. You need to understand about tunneling, which we covered. And then there is another process that has another method, another theoretical approximation that has been alluded to a couple of times called the strong field approximation. This one you also need to understand. I talked with some of you and learned that in fact some of you are not that well acquainted with the strong field approximation, so I'll try to cover that today in this talk. And then you also somehow have to do some classical simulations. So that's basically the theory toolbox. And if you master those things, you can work in this field. And we will see some of these different things today in this talk. And it's about dissociative ionization induced by strong laser pulses. And now what I want to show you here is that, in fact, you can think about H2 plus just to make it as simple as possible. And we want to place H2 plus in a strong laser field, and we want to look at how this breaks up when we change the wavelength from the midinfrared to the XUV regime, and see what we can learn there. Why do we want to do that? Well, overall, the aim here is to gain insight into quantum systems on the natural time and length scales with possible applications in the future in electronics and quantum information and material science. The central theme in all of this is, of course, this light-matter interaction. And I'd like to stress here that it's important to remember that everything we do here is really driven by experimental progress. And the pulses we have available are femtosecond pulses and attosecond pulses, and these can be used to probe electron and nuclear. So that sets the scene. But in order to be able to kind of apply this for interesting applications in the future, we still need to understand in detail the most simple and fundamental processes. And what I will show you here today is part of this, and the focus will be on ionization and breakup of H2 plus molecules. And since there is only one electron, the focus will be on the correlation between that one electron and the nuclear. And here is the outline. Breakup in static fields. This we talked about already in my first talk, so I'll just recapitulate a little bit. And then we'll talk about breakup in infrared and mid-infrared fields. And then finally in high frequency fields. And I chose this example because it's very good to illustrate some of those theory tools that you need to work in this field. You need tunneling. Here, it's TDSE, but the analysis can be conveniently done in this strong field approximation. And this one here, you also, of course, again need TDSE, the time-dependent Schrödinger equation. But also in this one, there is a new framework in which it's convenient to do the analysis, namely the so-called Kramer-Henneberg framework. This was introduced yesterday, and I'll do that a little bit more quantum mechanically today. So this we can go through pretty quickly. As I told you late the other night, this problem here of tunneling has been studied for many years for atoms and molecules that have fixed nuclear positions. And the new thing here that we have done here in this school is to ask the question, what happens if the nuclei move during the tunneling process? And one of the things we discussed the other night was this problem here, that I have my molecule here and apply a static field in this direction. Yes, indeed, the electrons are blue in this slide, so the electrons will be pushed down and the nuclei will fly out, right? And I mentioned that this is then mathematically what is called a Seeger state problem or a Gamow state problem, because in order to solve this ab initio, you need to solve the Schrödinger equation without going wave boundary conditions. And then there were some questions related to that. One consequence of this loss of probability of being in the ground state is that we get a rate. This is a tunneling rate. This describes the loss of norm over time. This you can think about if you just have a normal time evolution of some state, it will be e to the minus I dt, right? This is the normal time evolution of the state within E. And if you plug in this one here, you will see that this imaginary part leads to a decrease in the norm of the wave function of that component. But I found a few, I made 2 new slides here because I want to give you in these slides a place to look if you're interested in this Gamow or Seeger states. And in fact, a very nice paper is in fact Gamow's original paper published here in Madsen, but you can look at the equations. And this is about the quantum theory for the nucleus. And it has, in fact, 5 graphical figures. So this, at that time, was difficult to make, and here is one of them. And so he discusses various things. He discusses alpha decay, but he also goes through some examples, and this is one of them. And this one here, you can actually do. And this here is what we talk about outgoing wave boundary condition, and this necessarily leads to a complex eigenvalue. This is discussed very nicely in this paper. You can have a look. If you don't like the German language, you can have a look in for example, these 2 that I found in American Journal of Physics, a pedestrian introduction to Gamow vectors. So this sounds like something that is not too difficult to read. And there's another one down here. So please have a look in case you're interested. This was something that came up in view of your questions the other night. And coming back to the tunneling, I just remind you that we had this finding that for this tunneling process, the von Oppenheimer always breaks down. This was a little bit maybe counterintuitive for us. I guess if you ask the average strong field physics person the question, when do you think the von Oppenheimer approximation will break down for a strong field or a weak field? My bet is that 90% would say for a strong field. Because normally we're used to having a breakdown of the standard approximations when the field is strong. But in fact here, the point was that if the field is weak, we looked at this model here, one von Oppenheimer curve, another von Oppenheimer curve. We looked at this model and we saw that, well, we saw that the von Oppenheimer broke down, and the reason was what I recapitulate here. It's kind of easy to understand physical argument. Let's just go through it again. Here's the nuclear motion, the nuclear vibration motion scales like square root of the nuclear mass. Here's the exit point out here. It's dominated alone by the field interaction. So F times the exit point is the ionization. And how long time does it take for an electron moving in this field to reach that exit point? Well, we just use the standard classical mechanics here. 1/2 times force times squared times 1/2 times acceleration times time squared is the distance. And then I say if this time is equal to the time of nuclear vibration, it's clear that the electron no longer can instantaneously adjust to the nuclear vibration. And this is the physics of origin, and that's the reason why we found that we have an exact rate here as function of field strength, and then we have the von Oppenheimer approximation, and it breaks down at some point. So this was where we were the other night, and this covers what I wanted to remind you about tunneling, and more work is needed here, I would say. So now we come to the main theme of today, namely when we have a time-dependent field. And the questions we want to ask here were questions that were put up actually in that paper that Brett mentioned the other day, which was done in collaboration also with the 2 students. So you have some molecule here, and you put on a laser beam and you take the electrons and the nuclei. how is the energy shared between the electrons and the nuclei? What happens if one Oppenheimer function breaks down? Now you have both electrons and nuclei in the continuum. This is an unsolved problem. So there are some fundamental questions and issues related to this. And to understand this, what we want to do is that we want to identify an isotope. This was already, I like to use what Brett introduced the other night. I like to use this joint energy spectrum, so that will come up in a little while. Just to show a few equations before we look at the spectra. This is what we solve in this particular case. So we have a wave function depending on the instrumental distance and the electron coordinate. This is done in 1D. It's very tough to do this type of calculation even in 1D because you have this huge difference in time scale between the slow nuclear motion and the fast nuclear motion. You have the kinetic energy operator of the nuclei and the Coulomb repulsion between the two, and here you have the kinetic energy of the electron, and then you have the attraction between the electron and nucleus A and attraction between the electron and nucleus B. And then I put something here, I'd like to emphasize this in case some of you ever want to do a calculation like this. This is, when you do 1D TDSE calculations, it's important to smoothen the Coulomb potential. This is what this factor does. And this, often people put 1 here. That's fine, but if you put something that is a function of R, what we gain by that is that we can then in fact get the correct von Oppenheimer curve. In a 1D model, we can still get the correct ground state von Oppenheimer curve by having a smoothing parameter that depends on the internuclear distance. So this set of equations here was solved, and we looked at the energy sharing between the electrons and the nuclei. This is this simple here. What is the probability that the electron comes out with electron EE and the nuclei come up with electron EN? And there's a formula here. We just have the wave packet at some instant of time after the pulse, and then we have to do a projection on those energy states. This is like Born's rule for quantum mechanics. And this is what we found. We found if you plot here the energy of the electron and here the energy of the nucleus, you find those lines here, or these lines with maxima along these diagonal lines here, and that corresponds simply to this nice formula that we also saw the other night. We start in some initial state. In this case, we start in some initial state which is vibrationally excited, in this case 7, and we absorb a certain number of photons, and all these photons are then given to this quantum system, but it's shared a little bit. The electron can take something, and the nucleus can take something, but it has to be in accordance with energy and conservation along these lines here, right? I hope that's clear. And then there's this ponderomotive shift on top. So now, I would say that this joint energy spectrum reflects a strong electron-nuclear correlation. Why is that? Well, the laser, as you saw from the TDSE here, only couples to the electron, right? And then the electron takes the energy, and then the electron disappears, and then, I mean, how this sharing occurs depends on also how the electron interacts with the nuclear system. Moreover, we see that, for example, we can have a case where if we take this maximum here, this particular photon absorption channel, you can have a case where if you go up here, it means that the nuclei more or less take all the energy of the electron is very small. So this kind of PT here gives you some insight into how the energy is shared and how the correlation is in the system. So if you go down here, the nuclear energy is more than the electron takes most of the energy. And as also mentioned by Brett, this has been verified experimentally. These things here are seen in the case of circular polarization and also in the case of linear polarization, as you see here. So it seems that everything is actually quite nice, and it seems that if we look at this spectrum, energy of the electron, energy of the nucleus, we have these diagonal lines here with maximum corresponding to a given photon absorption. Yeah.
So do you expect some discreteness? Large lines, because if it is the sharing between electron and the ion, it is continuous.
I think I didn't hear the question, but what this manifests is this formula here.
Right. So is there any preference in terms of the sharing of the energy?
And this is for example, let's focus on this one here.
Mm-hmm.
I can't remember how many. I don't remember the end for this one. It's maybe 4 or 5. I don't remember. It's not so important, but you have absorbed some photons here, right?
Yep.
And then if you go along here, you can see how that energy is shared. Because the more red, it's the more likely. So, for example, it's more important that you have a measurement here with this electron energy and this nuclear energy than a measurement up here with this electron energy and that nuclear energy, in that sense. So this is the picture based on this formula here, meaning basically that we have a result here which will be like En plus EE is some constant along one of these maxima, right? This is what this figure shows. And is that the end of the story? Well, in fact, it isn't. And that this is. I thought this would be fun to show because it turns out that we also sometimes see structures like this, and which would somehow a priori conflict with energy conservation. What is going on here, right? This is energy conservation, and now I'm saying you can also get subscribes. So what do you think this is? If you get kind of crazy non-classical results, what would it be? Quantum mechanics. Interference, yes, very good. And it doesn't end there. If you vary the laser intensity, you can also get subscribes here, meaning that it's like fixed energies of the electron. Right? So this is the aim here now for the next couple of slides is to show you that this is in fact seen, and then to explain why this comes about. Okay, so that's, and this is of course, I mean, I hope that you realize this is somehow strange. This is energy conservation. What is this? Let's just see the figures showing this. If you want to have a look, we put this on archive. And Lun Yu did this work, a PhD student. Here you have this is the old result, more or less. It's a slightly higher intensity where you have these lines here at 400 nanometers of driving field. Just focus don't focus on this stuff over here for the time being. And then we increase the wavelengths to 800. Well, it looks a little bit messy in here. It's more complicated. It's due to interferences. But out here, you have these nice diagonal lines. If we increase the wavelength even more, we get what I tried to draw here on the center of the black hole. Namely, it seems that we get something that goes this way, kind of what I would refer to as cross-diagonal lines. But in fact, at the same time, we also have something that goes this way. So how can that be? These inserts here show you a magnification of these areas, and they show you, in fact, electrons going to either right or to the left. So, to understand that, we need my handwritten slides. Yeah.
In the former slides, what gives this why does this origin? Why does it origin?
Huh?
What gives the widest origin?
What gives the width?
Yeah.
It's the bandwidth of the laser comes into play, like in the other case.
But here for the one 1,000 and
So you see this distance here is the photon. And here's the photon, and up there is the photon. So if this is 1.5 eV, you can multiply by 2 and divide by 2 yourself. So to understand that, I thought that, yeah.
So, am I seeing your picture right? I mean, it looks like you still have the energy conservation, conserving lines still there. There's just other patterns superimposed on top.
Sure.
Okay, so the energy conservation doesn't go away.
No, there's other patterns. But if you look, if you didn't know about this, I'm just trying to,
Sure.
I think it's called in modern language to create a burning platform. Right? I was trying to, but I don't think I succeeded very well. But anyway, you're absolutely right that there are still these energy conserving stripes, but there are other features on top. If you didn't know about these energy conserving things, I think you would just say, well, this is like dominating trace. So there are other things on top, and this is, I mean, in the general, what's the point? This looks like very special. In fact, it's not so special because the point here is that when you do this strong field physics, it's extremely difficult to predict because for one set of parameters it can look like this, and if you change the wavelength, it's completely different. So you have to be extremely cautious to make conclusions based on some studies that have been at 800 nanometers and then infer how it looks, for example, at 1600. To go to this is beginning to be, I would say, extremely interesting. And this is one of the things we're struggling with technically, because the longer the wavelength, the more difficult it is to do the TDAC calculation. So many of us are kind of inventing or trying to extend or invent new techniques to go even to like 3,200. So here in this school, it's good to have a look at this strong field approximation because I want to interpret some of this using a strong field approximation. Okay. So let's just recapitulate the strong field approximation. It's something to do with getting a matrix element from measuring an electron with momentum k. And for doing that, you need the wave packet at some time t larger than the pulse, and then you need to project in a scattering state. At this point, there's no approximation. This is just normal quantum mechanics. And then to discuss the strong field approximation, it's nice to do that in terms of the time evolution operator, which is this u here. So this wave packet at time t, I can get from the initial state at time t naught with the time evolution operator, u. That's also well known from quantum mechanics. And I'll give you some expression for this on the next slide. The point I want to make now is that the full Hamiltonian is kinetic energy, potential, interaction with the external field, right? This we can split in various ways. And here is one way of writing it. This is the kind of standard perturbation theory way. I give you some H naught for the system, and then I add something. This is what we do also in quantum optics. But we can also split it in a different way, namely, well, if now this laser field is very strong, or if the electron is far away from the potential, maybe it's better to try to describe this as accurately as possible, and then treat this as a perturbation, right? So you see, it's the same Hamiltonian, but the point of view is different from here and here. And this is the whole idea about this strong field approximation, because you want to start in a state where this is dominant, and you want to end up in a state where this is dominant. And by the way, this HV here, I put a V here because it's called the Volkov Hamiltonian, and it can be solved analytically. It's very easy to solve. And here I write, this is the equation, and here I write the solution. And you can easily check that this is a solution in space representation by inserting the energy line. This particular solution is in the velocity fields, but it's not so important. To come back to this, the idea is that we can split this in different ways. Therefore, we can also probably split this time evolution operator in different ways. This is what we do in this slide. It may be a little bit fast, but the idea here was that now you will have these slides, and you can look up anytime you like and see how you can do the SFA. We have an equation of motion for the time evolution operator for the H0. We have a time evolution operator for HV. We have the full time evolution operator. These are the Schrödinger equations for the time evolution operator. And now the only new thing here, or I don't know if it's new. It's maybe new for you, but what you need to know is that you can write the full time evolution operator in this way. So the full time evolution operator can be written like the time evolution operator for the H0 part minus I integral from T0 up to T over this thing here where you propagate from T0 to T prime, interact with the laser field at T prime, and then propagate from T prime to T with a full time evolution operator. This is one way of splitting the potential, or alternatively you can propagate from T0 to T prime in the Volkov propagator, interact with the field, with the potential, and then the full time evolution operator taking you from T prime to T, and then out here you have the Volkov propagator. So those two things are equally exact. To see that these two guys are exact, you have to insert here. And then you have, when you do the integration with T, you have to remember that you have T here and you also have T here. So sometimes this can be difficult, but I can help you if you want. So, what is now the SFA? The SFA is simply that you take the first one here, and then at this position here, you put in this equation. This is the SFA. So at this position, I put in this one, but I neglect this term because the potential is in higher order. So effectively, it means that at this position here, I only have the Volkov propagator. So this here is the SFA time evolution operator. And this is the time evolution operator that I then use here. And the other thing I do together with the SFA is that, you see, here I have thrown away the potential. Then to the same order in the potential, it's also consistent to, instead of using the exact scattering state, use a plane wave. And with these two things, you get the SFA amplitude. And the only thing that is extra compared to kind of standard is to remember the spectral decomposition of the Volkov time evolution operator in terms of the Volkov state. So I hope this was helpful. I like to do it this way. It's very transparent with the time evolution operators, and you can now, if you like, you can play around with iterating to higher terms, and you can get the interaction with the potential and the rescheduling and all this stuff. So now at least you have the possibility to revisit this. So where were we? Yes, we were discussing, in fact, this time of the same things here, and I wanted to do I wanted to use the strong field approximation for this analysis. And here is the strong field approximation, initial state interaction with the field, which is now called VI instead of VF, but that's how it is. And here it is in the velocity gauge. And here we have the final state, which is now more complicated because we have a wave packet for the nuclear degree of freedom and one for the electronic degree of freedom. When you look at this, you can collect kind of the phase factors in this interval and the rest. And you see here that you have this A here in the exponent. Maybe you don't see it. It was somehow, it's here. This is the phase here. You have this huge phase in this Volkov state. And this phase is very big. And if you want to do integrals over integrals with rapidly oscillating phases, where do you think you pick up the main contribution? Yeah, you pick it up when the phase is slowly varying. So this is what we do here. We do some saddle points, and then instead of having a time integration, you just have a sum of some saddle points corresponding to stationary phase, meaning we find the TS's when the derivative of this phase is 0. And then using this so-called saddle point technique, you then get the rest here also. If you wonder where to read about such things as the saddle point technique, I normally tell my students to have a look in this book here. Afghan has a nice book on the mathematical methods. It's worthwhile having a look there. And moreover, in fact, okay, you can also ask me for some more notes. I have a lot of notes on this topic. So now we're almost there. Because now we have this sum of all these times here, all these saddle points. And these saddle points, in fact, of course, reflect when this ionization takes place. So we have the pulse here analysis to have in mind was published in the case of atoms by AMO and others in 2010. And they have in their paper this figure here, where you have the red curve is the vector potential, and the black curve is the electric field. Let's look at this part here, where ionization from this instant of time and from this instant of time will give the same final vector potential. This is what Buxbaum talked about yesterday. We have two events in this part of the cycle, in this so-called, there's another word that is often used in this so-called simple man model. You say that the final momentum of an electron ionized at time t I, for example, is obtained by the integral over the electric field like this. So you just neglect everything else. And what is this? This is nothing else but minus the vector potential. That means that these two values here of the vector potential contribute to the same momentum. They should be added coherently. And what you see here from this one here is that you have things that happen within the same cycle. So you have two contributions within each cycle. They are called intracycle, and contributions between different cycles are called intercycle. And this we did, now I think I want to show you that also. Why not? So here. So this is now from Lund's thesis. It's just to give you, I don't want to go through all these equations, but please focus over here. We're considering some matrix element, and we were having these phases here from the intracycle contributions, and we made to do this, to do the calculation which is necessary to make the interpretation, we need to define the average phase and the phase difference. And when you do that, you can write the probability, which is this sum of all those saddle points, and you can introduce those two things, namely the average phase and the phase difference, and then you can separate out a contribution coming from the phase difference, which will be intra-cycle things, and then the rest, which will be intercycle things. So this thesis will be online when he will submit in the end of this month. So after that, you can find it on the internet. So this, I hope at least somehow I gave you a feeling about how you can do this sum here, leading to basically an intra and an intra-cycle contribution. And this is now the result here. Here you see the full SFA at 400 nanometers, 800 and 1600 nanometers. And what you see here is kind of, you find some of the features which were in the TDSE calculations, right? And then I have plotted here separately the intra and intercycle interference effects. So this is one, and clearly you see here the intracycle one, you get these energy conserving diagonals, and the intracycle things, you see those things that look cross-diagonal and maybe at odds with the energy conservation. But it's an interference effect, and it's a nice challenge. Maybe you could try to think. I didn't discuss this with Brett, but maybe one could think about how to interpret this in terms of this carrying with a phase picture. In any case, so these are the. So now we have covered this one here and this one here, and in fact this one here can also have. And this is what I show you here in the next view graph. What I have, so here you see now in this case, the energy of the electron is kind of very confined, and then you have some broad distribution over nuclear energies. how to understand that? Well, this is now showing that you can have just, so the only thing I did here was that I decreased, this is also 800 nanometers, so what I did was that I decreased the intensity a little bit. So at higher intensity, I got this result here, and now I decrease the intensity a little bit, and then suddenly I get this result. So why is this? So this is now more difficult, because to understand this, you need to look much more carefully into the dynamics. I don't think it makes much sense here to go into the dynamics in detail, but I can mention that in order to explain this and this fact that the electron seems to be discretized in energy is because at lower intensity we cannot readily ionize in from here. We need to dissociate a little bit before we can ionize. And where we can do the ionization, we have in fact pretty much parallel curves. This means that that it doesn't depend on the internuclear distance and not on the nuclear energy. And that's why it suddenly looks like this. So maybe some conclusions at this point. At low frequency, we have talked in my lecture here about tunneling, and we have talked about the joint indie spectra and intracycle interference. I should mention that this, I mean, this was predicted in atoms, but it's not really been very clearly observed. But it's clear that if I could convince someone to do such an experiment in a molecule, there should be extremely clear signatures of this effect. So now, there are many other things that you will meet in the literature when you look at strong field dissociation, so you will see all these terms here. I cannot possibly cover that, but there's a lot of different physical processes going on. Rather now, in the last part of this lecture, I'd like to take you into a kind of regime of the future a little bit, because new technology actually means that we can produce femtosecond pulses with intensities that are exceeding the atomic unit of intensity, and with photon energies above the ionization threshold. So this is a new regime, and how does breakup occur in this new regime? So that's what we wanted to ask about. So what is the characteristic breakup in that regime? So let's start. Again, I showed you this equation already. It's the same equation we solved. And there are some observations. Observation number one is that stabilization occurs. What is stabilization? Well, here what you see here is that this is the probability for ionization as function of the field strength, amplitude, so amplitude also, and for a fixed frequency in atomic units. And stabilization is this effect that you have a non-monotonic behavior of the ionization probability as function of field strength. Of course, you would assume that the more intense you make your pulse, the more ionization you will get. That's kind of the convention of tradition I expected. But since, I think, the 80s, it has been known that you can have something called stabilization. And stabilization simply means that you have this decrease in the ionization yield as function. So this is one thing you can have. The new thing here, compared to what was known, is that this is now done in a molecule. So you can have stabilization in a molecule, including nuclear motion. What happens then here when you have stabilized the ionization? Then the other new observation is that you can then have a big dissociation probability. And this is what is shown here. Again, dissociation probability versus field strength. And you see at low field strength it's unlikely because you ionize, but then as you increase the field strength you can have a lot of dissociation. So how can that be? So this all came out of our TPSE calculations. And then the when you do theory based on the TDSE, the job is like doing an experiment. Then we still have to do some other theory to make an interpretation of what came out from the TDSE, at least in some cases. And to do that, we need to go through this slide, which I also prepared yesterday evening. It's because this is better done in another frame, which is a non-inertial frame, which is called the Thomas-Henneberg frame. And then I thought it would be good just to make sure that you know how to shift between different points of view. You have the length gates where the electric field interaction is field times r. You have the velocity gauge where the electric field interaction is a dot p. But you also have other things. And all these things can be generated using these two lines here. If I have a time-dependent Schrödinger equation looking like this, I can define another one, psi prime, which is nothing else but some unitary transformation, a unitary operator times psi. So in this slide here, u is not the time evolution operator, just the unitary operator. If now I isolate psi from this equation and plug it into the original time-dependent Schrödinger equation, I get a new equation. This is left as an exercise for this new psi prime, where the Hamiltonian is transformed like this. So you have a unitary transformed thing here, and then you have this term here, which involves time dividency. In some courses in quantum mechanics, students learn about this. In some, they don't. How many have seen this before? Okay, it was worthwhile to show it. And what is the point? The point is that now, typically, we have this equation here, I dt psi velocity gates representation, where you have this interaction term. And then, in fact, you can get this one here, called Thomas-Henneberg, by using this rule up here and this operator. E to the minus I alpha dot p, where alpha is the integral of the vector potential. And then to evaluate this explicitly, you see that you get like, for example, in here you would get e to the minus I alpha p of r, and then the Hermitian conjugate of this operator. So you need somehow to be able to do some commutators of some operators. And there's another thing you have to look up in your quantum mechanics book called the Bayer-Hauser operators. I wrote it down here for two Hermitian operators, D and B. So with these tools, you can basically get from this equation to this equation. And except that I apparently miss a parenthesis here, it's correct, and it's the expression for the interaction in the Thomas-Henneberg frame. And you see here, suddenly the interaction with the external field somehow disappeared. Explicitly kind of disappeared as a term, as a direct additive term in Hamiltonian, but it came in here in the potential. So what it means is that, for example, if you had the Coulomb potential, we use the equation there, then it would be minus 1 over r plus alpha of t. Right? So if I had the Coulomb potential looking like this, say without any external field, then at some instant of time in this field, I would have shifted the origin. Right? So maybe at some instant of time, I would have the origin here, and so at other instant of time, I would have the origin here, and so on and so forth. And this is what we do. So it's instructive to transform the TDSE into the Thomas-Henneberg frame. So the point here was that it's not because we needed to do that for this our small problem. It's because it's good to know how to do it, and you can often benefit from this picture also in your analysis of any result. Here is it looks a little bit more complicated now with some factor beta here that depends on the masses because we have the molecule. And now we have this potential here. And then the final step is to say that, okay, this potential here, which is the potential of time, I can decompose into Fourier components. Right? And if if alpha here is very big, this quiver motion. So maybe I wrote it here. So this the dimension of this here is momentum. So if I integrate momentum, I get physical displacement. So if alpha here is very big, it's not goes like this. And then if it goes very, very fast, then of course the n equals 0 term here in the potential dominates, right? And this is this potential here. This is the dominating term in this Fourier decomposition. So this here is the dominating term. It's just a time averaged Kronos-Henneberg potential. And therefore you're led to a structure equation. So you're led to a structure equation involving kinetic energy of the nuclear and the Hamiltonian of the electronic part with this time averaged potential. And doing this, we can obtain new Dress-von-Oppenheim curves. And this is what I show here. So this is also something you will meet a lot when you discuss molecules. Maybe not Dress-Kronos-Henneberg potential curves, but Dress potential curves. And here's one example of such Dress potential curves. And in this particular example, I have this curve initially, and then I have now, let's say, this one here finally. And the dynamics at play here, the dynamics that explains that I could get so much dissociation is actually explained in this view graph. Because initially, I have this system here, I increase my field strength, I get a Dress-von-Oppenheim curve, I increase the field strength even more, I get this one up here. It's above the limit of dissociation. And the way I manipulate the laser in this particular case is such that this state can more or less follow adiabatically up. But once it's up, the time scale of the, you see the energy levels here are decreased compared to the energy levels here because the well is wider. The nucleus now moves slower. It doesn't have time to come back again when the speed is switched off. So kind of simplistically, it follows up adiabatically, but then when it's up there, it's moving too slow to follow down again. And then it's suddenly trapped there, and this field is gone and it moves out. And this leads to dissociation. And this picture you can use in many cases like this. So you can have it here. In this case, the pulse is very short. It's so short that the nuclear wave function doesn't have time to follow. In this case, this is the case we just discussed. In this case, the pulse is very, very long. So in this case, the nuclear wave vector has time to follow up and down. And this you can do for cases when you have a field strength or corresponding to a given quiver amplitude, which is proportional to the field strength. You can have both above the threshold for dissociation, but you can also have it below. So in this sense, this can be controlled. And it is, in fact, this is kind of the model. And this model comes out from the TDSE calculations, where we show, again, field strengths on the x-axis, and then here we show vibration quantum numbers for the bound state and the nuclear kinetic energy for the continuum states, and we do this for different cycles. Very long cycle, very short cycle. For the same, and if we just remember my picture here from before, I said if the pulse is very long, this wave packet will follow up adiabatically and adiabatically down. This is in fact what you see, because after the pulse, we only have population in the vibration ground state for this very long pulse. When the pulse is shorter, we have some vibration excitation. In this picture, it's like it goes up, but it can't really follow all the way down. And over here, if the pulse is very short, we just have a little bit of sudden excitation of the vibration states. And this case here is the case when we can have a lot of dissociation also. So to put this in a more general framework, so it's good sometimes to think about Dress potential energy curves. In this case, in the Kronos-Henneberg frame, it could be other kind of Dress potential energy curves, and then try to make an interpretation in terms of that. And another central topic here is this issue about timescales of the nuclear motion in this case. What is the timescale of the nuclear motion compared to the timescale of the when you change your field. So the field could be sudden from the point of view of the nuclei, but not sudden from the point of view of the electron. Okay, so what we have found here is that stabilization against ionization occurs. Dissociation may completely dominate over ionization in this machine. And the vibration distribution, dissociation yield, and nuclear kinetic release may be controlled by pulse parameters. Because if the field is not sufficiently intense, I can trap the population in some vibrationally excited states. Okay, so at this point, we have seen a lot of examples of electron-nuclear correlation. What we have not discussed, because in fact I only discussed H2+, is how do electron-electron correlation affect strong field and attosecond physics. For example, what is the validity of those models we often use? What is the validity of the single active electron model, the two-step model, the three-step model, and so on? So this is going to be the topic of my last lecture tomorrow. So now we have learned a lot from single active electron models. We know something about electron-nuclear correlation. How should we add electron-electron correlation, and what will we learn about it? That's somehow the topic for tomorrow. I think that's it, because I skipped this. You have had enough, I think. Yes. Thank you very much.
Thank you very much.
Could you just clarify this stabilization? When the stabilization goes down, that seems to be exactly when the dissociation increases.
Yeah.
So it's stabilization in an unusual sense, which the target is changing.
Yes, so just to show how I understand the question. So this here was the first figure showing ionization probability as function of field strength. It goes up and stabilizes. And you see this starts to stabilize around here, you would say, a peak here and then stabilize. And then we go to this one, maybe stabilize here.
Yes.
and then this one goes up, as you point out. And it's true that to see this effect, to see this huge increase in dissociation, of course you cannot afford that the system ionizes. And that's your point. And therefore it's also clear that it has to be under some kind of exotic conditions, because in any normal system, I guess you would have more resonant ionization process than you would say than this highly non-resonant dissociation process. But one should not be led by that kind of standard. I mean, if you think in terms of a few photon process, if you stack one photon on top of that curve and say clearly it ionizes, this is the resonant one, and the dissociation is very non-resonant. But the central point here is that then to understand this mechanism, we actually need to go into this Kamasenan frame and think in terms of these stressed monopole. And then you would say, what happens then if I do not have a single electron system? And this is a very interesting question that requires more work for the future.
There are still two ways of interpreting this. You could say, well, you have the molecule, and you can ionize it, but this stabilizes, and so you have a certain fraction of the target that's not ionized. But you would say another fraction is dissociated, sort of two separate things. But if you think of a single molecule, then it becomes more difficult how you define stabilization if it's dissociated.
Well, I mean, the definition here is that dissociation is when the final state is a proton and a hydrogen. And ionization in this one would be 2 protons. Yeah. And
So let me try this. So what I think of Renner Anderson stabilization is I have an electron oscillating. Sort of I like to think of like that. Oscillating off to the side, and of course it's best bound if its extrema is near the nucleus. So by adiabatically moving the bucket, and by letting the system evolve adiabatically, are you moving the electron essentially out of its bonding position between the atoms, pushing it off to the side where it's wiggling like that, and then you let it free, the electron is no longer turn on the field, the electron is out where it was binding the wall. Could it be fit in this physical way? Not sure it's very articulate.
no, actually, I cannot. Maybe, I don't know. It's certainly what you're saying is different from what I give here.
Well, I'm not sure it's different, that's fine.
Yeah, well, this is.
You said you adiabatically.
Yeah, so this here is the curve for a given field strength. Then I increase the field strength. Then I have this curve. Then I increase the field strength even more. Then I have this curve. And this is actually the vibrational ground state density in that state.
So it's adiabatically changed.
So this is how it's changed. But of course, this curve doesn't say anything about how the electron moves in itself, because this is the solution that comes out from solving the electronic problem.
I wonder if that's what actually happens.
Yeah, I mean, it is in that sense that to the extent that this, what you say, is of course reflected in this counter-twin frame. Yeah. And it seems to me that what you say has more to it than what I could answer now. So let's discuss that.
Yeah.
Since you're solving the TESE here, I assume that it's the 1D H2 plus.
Yeah.
Well, we also know that stabilization, all of that is exaggerated in 1D compared to 3D. So how do you expect this to survive when you go to a real 3D problem?
Yeah, this was this we addressed a lot in this, this one. In fact, there is and this was we had very constructive comments from a referee, or actually from 2 referees, and they were both constructive. And they asked about this, and they asked about what if now I have a multi-electron molecule. And those issues are discussed in the end of our lecture. And the brief answer is that you also have this effect in 3D, and you also have, some people have in fact done this type of calculations for 3D molecules and find the same trend. This was done in the 90s by a French group and also from Gabriela and collaborators. So we expect that this could occur. So for this mechanism to run, you need some degree of stabilization, and then you also need, and this is what we're investigating now. But it's clear that it's not. If now you have, so can I answer quickly? So now just to make clear, here's the ionization potential. And this now here is some simple picture of some atomic or molecular system with more than one electron. So this is a mean field picture. If these guys here are stabilized, it maybe requires that the photon energy is like this. So now it was a bad one. Down here I have some other states. And this may be, the valence may be stabilized because the binding energy is less than the photon. But now you can see that maybe in this particular case, I could go to the continuum with a 3-photon process. So if it's not good for us if the valence is stabilized and I have that's bad wording. It's very interesting to think about what this then means, right? So we have a competing multi-photon ionization channel from an inner shell. It's occurring simultaneously with some dynamics of the outer one. And this this physics here is something we have to begin to take serious because this was the motivation for this work, because these pulses are being produced now. So all this stabilization was discussed a lot some years ago, but I think now we have to look at that. We have to look at this pulse regime.